So we are continuing with section 10.1. We've looked at how to find parametric equations for lines, and then also for circles and ellipses. In this little part, we're going to talk about how to find parametric forms for other curves. In general, unless we recognize one of those special cases, either the line, the circle, or the ellipse, the easiest way to parameterize a curve is based on the type of function notation you're given. If you start with y as a function of x, then typically the simplest thing to do is just let x be the parameter. Let x be t, and then y would be f of t. Conversely, if your original curve is given where x is a function of y, like x equals g of y, in this case, just let y be t. And then x will turn out to be g of t. These are usually pretty straightforward parameterizations. So take a look at example 9 here. We've got the function y equals x cubed minus 3x from 0, 0 to 318. We want to find parametric equations and sketch the graph. So I'm going to start by saying, since y is a function of x, if I simply let x equal t, then I can plug t in for the x's, and y is t cubed minus 3t. Since x is t, I'm going to use these x values to limit my t's, so I only get a particular portion of this curve as t goes from 0 to 3. All right, in terms of graphing it, just to kind of let us think this through a little bit, right now I'm just in standard function mode, and I'm just graphing y equals x cubed minus 3x, the original, just to give us the picture. It looks like that. So I'm going to sketch that. Like so. All right. In order to now limit myself to just the portion of that curve that I want, between 0 and 3, I'm going to make myself a quick little table. When t is 0, x equals t, so x is 0, and y would be 0 minus 0, which is also 0. So that tells me I'm going to start here at the point 0, 0. At t equals 0. Now my ending value of t is 3. X is t, so that's still 3. And for y, I would have 3 cubed, this is 27, minus 9 would be 18. So when I get to the point 3, I have to go up a ways here, 18, that's going to be my ending point. And that's at t equal 3. So in fact, I don't have the entire graph. I really just have the portion between the start and end points. I start at t equals 0, so this is the direction of increasing t, like so. The full graph, of course, continues on beyond that and continues this way, but my portion is just that part. All right, let's try this next one. This time, my graph is x equals minus y squared plus 3y plus 10. And that goes from 0, negative 2 to 0, 5. This time x is a function of y. So this time I'm going to let y equal t. And then I can just plug in the t for the y's in order to get x. I'd get minus t squared plus 3t plus 10. Since the y values are the t's this time, my t's are going to go from -2 to 5. All right, this time, last time when I did this, remember how I just went ahead and plugged in the original function, y equals? Your calculator doesn't do x equals equations. Desmos does, but if you're on your calculator, it won't do those. So parametric equations makes a really nice way to get this function graphed on the calculator. So I'm going to go back into parametric mode here. Oh, shoot, hang on one quick second here. All right, I had some functions typed in here already that I want to use later, so I just kind of de-emphasize them. Look at where I'm typing the new ones now. You can ignore everything up here for now. I'm just going to put in my parametric equations. X equals minus t squared plus 3t plus 10. And then y equals t. I'm going to go ahead and in my window, just because I want us to figure this out kind of for ourselves, I'm going to go ahead and do like a -10 to 10 for the t values. And I'm going to leave my x and y as -10 to 10 as well. Although we could have put in our limitations on t. I'm going to make us figure that out for ourselves right now. So there we go. Looks like it's a sideways parabola. I didn't quite see far enough to the right, so I could change my window to go for some slightly larger x values. I'm going to go out to 20 on the x. And there we can see our picture. Kind of like that. All right. I would like us to think through the process of the starting and ending points by thinking about the t values being -2 to 2. And so if t is -2, then y is -2. And I'd have to plug the -2 into this to get the x. That gives me 0 for x. I want to stop at t equal 5. So again, the y value is the t value, that's 5. And if I plug 5 in for the t up here in the x, I get 0 again. Therefore, the portion of this parabola I'm interested in goes from the point 0, -2, which must be down here, I start here at t equal -2, and it ends at 0, 5. So this must be at a height of 5. This is where we end at t equal 5. And I'm therefore looking at the portion of this parabola between those 2 points. I want to go in the direction of increasing t, so I'm going this way. All right, so that's kind of how we handle situations where our functions are either defined as x equals a function or y equals a function. The next thing I want to look at are situations in which we're given the parameterization, and we'd like to see if we can figure out what the original xy form would have been. So in example 10, I have a curve defined by the two parametric equations, x equals t squared plus 4, and y equals -2t squared plus 1, between -5 and 5 for t. Okay. I'm going to try and go backwards this time. I would like to see if I could figure out what the xy equation looks like. The little hint up here, we're trying to eliminate the parameter, eliminate the t. So think about those old substitution and elimination methods that we know. And my goal is to take these two equations and eliminate t. That way I'll have an equation with just x's and y's in it. So let's see here. I have x equals t squared plus 4, and y is negative 2t squared plus 1. In this case, I can see that it would be fairly easy to get the t squared terms to cancel if I just multiplied the top equation by 2. So that's what we're going to do. 2x equals 2t squared plus 8. And then we'll keep the bottom equation the same. If I now add those together, the left-hand side is 2x plus y. And on the right-hand side, by design, the t squareds are eliminated, and I just get 9. So there's the equation in its xy form. And, perhaps somewhat surprisingly, what would the graph of that equation look like? That's just a line, right? Kind of surprising when we started out with t squareds in there. But after eliminating the parameter, we find that all we have is the equation of a line. In fact, if I wrote it in slope-intercept form, y equals negative 2x plus 9, it would be pretty easy to graph. Y-intercept of 9. Slope of negative 2, which is going to make this go at, what, 4.5 down here? And there's my line. I didn't get that one started very well. All right, we specifically wanted to be for t values between negative 5 and 5. So let's see if we can figure out what portion of this line I'm really looking at. So if I start with t equal negative 5, x, remember, is t squared plus 4. So 25 plus 4 would be 29. And y, that'd be negative 2 times 25, negative 50 plus 1 is negative 49. I'm going to deliberately leave myself some space because look what happens when you plug in positive 5. Nothing changes, right? Because of the fact that when you square a positive or a negative 5, you end up with the same thing. So x is still going to be 29, and y is still going to be negative 49. So, do we go anywhere? Well, we do. Just to kind of see what happens, I'm going to also plug in t equals 0 in the middle here. And notice that when t is 0, x would be 4, and y would be 1. So what's happening is we're starting at the point 29, negative 49. We're traveling to this point 41, and then we're traveling back to the point 29, negative 49. Now, I didn't make my original graph quite big enough, so I'm going to draw myself another one here that has a little bit larger values on it. Let's see it. Sneak it in over here. I start at the point 29, negative 49, so let's say that's about here. I travel to the point 41, so maybe about here. And then I travel back. So I'm only using this portion of the line, but I'm traveling both ways. First, I go in that direction, and then I come back in this direction. I go both ways along that line. There's something else kind of interesting that happens with this parameterization, and I'm going to show you a Desmos graph to illustrate that. So what I've got here is my line, y equals negative 2x plus 9, and notice I've used a nice big window so we can see that those points, this is actually at t equals 0 right now. We've got our point 41 right there. And I've clearly made it so that the point 29, negative 49 is going to appear on my graph. Watch the animation as I let this parametric equation, as I let that little point travel along the line according to this parameterization. Notice how it does go up and back. Let me start this over one more time. Last time I pointed out we started out at 0, but I want to start it at negative 5. There we are at negative 5, at that point 29, negative 49. If I go ahead and move this along until I get to t equals 0, there I am at that point 41. And then if I continue to go back to t equal 5, I end up going all the way back down to where I started from, 29, negative 49. So this is a line that we've traveled back and forth along. I'm going to animate this one more time, and this time I want you to pay attention to how fast or slow the point is moving. Do you see how it slows down up here and then goes faster when we get down here? So it goes, let's see, start from the beginning. Quick, slow, quick again. We're traveling at a variable speed along this line. And that's what parameterizing a linear function, but using the t-squared terms in the parameterization, does for us. It allows for a variable speed as the point travels along that line. Kind of cool. All right. We have another eliminate the parameter problem. This time our curve is defined as x equals 1 minus sine squared t and y equals cosine t as the t's go from 0 to 2 pi. Oftentimes with trig, the unfortunate truth is we need to use some trig identities to help us out. And that's what the case is here. I'm going to have you notice that 1 minus sine squared t is just a form of that famous trig identity, the Pythagorean one, right? 1 minus sine squared t is really cos squared t, right? If I move the sine squared to the other side, I'd have sine squared plus cos squared equals 1. So in fact, what's going on here is if I take the y equals cosine t and I substitute, I can plug y in for cosine t. What I really have there is y squared. So I've just used a substitution method. X equals y squared. Well, I know what the graph of x equals y squared looks like. Y equals x squared is just the vertical parabola. X equals y squared is just the horizontal parabola. You can verify with your calculator if you want to. But it just looks like this. Now, since I've got 0 to 2 pi as my interval, I don't have the whole parabola, I just have part of it. So let's go ahead and see if we can figure out what's going on here. I'm going to make myself a table of values. And I'm leaving myself kind of a lot of space, you might have noticed, because I kind of already suspect that there's going to be an issue. 0 and 2 pi in trig terms are the same place on the unit circle. So I think I'm going to get the same answer for both those points again. But let's verify. If I start at t equals 0, x would be 1 minus 0 for sine 0. That's 1. And y would be cosine 0. That's also 1. So I started times 0 at the point 1, 1. I'm going to go way down here because I'm going to try and put some things in the middle. If I go to 2 pi, my ending t value, the sine of 2 pi is still 0. So I have 1 minus 0 or 1 again. And the cosine of 2 pi, just like the cosine of 0, is 1. So the point 1, 1 is both my starting and my ending point. Just like last time, start and end at the same point. I probably go somewhere in between, however. So like that line problem, we're going to probably go someplace and then return. Let's see where we go. I'm going to go ahead and plug in pi halves, pi, and 3 pi halves to kind of figure out what happens in the middle there. At pi halves, the sine of pi halves is 1. So I'd have 1 minus 1 squared, or 0. And for y, the cosine of pi halves is 0. So I've come to the point 0, 0. Definitely have traveled. What about pi? Sine of pi is 0, so 1 minus 0 is 1. And for y, cosine of pi is negative 1. So now we're at this point 1, negative 1. This was t equals pi halves, and this was t equal pi. Keep going. 3 pi over 2. Sine of 3 pi over 2 is negative 1, but squaring that's going to give me 1. So 1 minus 1 is 0. And the cosine of 3 pi over 2 is 0. So now I'm back here to the vertex at 0, 0 again. So here we once again are at t equal 3 pi over 2. And then of course at 2 pi we're back to 1, 1. So we stay between these 2 points, but once again we're going to travel it both ways. We're going to go down to the 1, negative 1, and then we're going to turn around and we're going to come back to the starting point of 1, 1. I would encourage you to play around a little bit if you want to on Desmos to see that, but it's the same kind of thing we saw before with the line. You start here, you're going to travel down, and then you're going to travel back again. All right, and one more eliminate the parameter problem. We've been given x equals e to the t plus 1 and y equals e to the 3t. T values from 0 to ln2. And once again, we'd like to kind of sketch the graph of this by first eliminating the parameter to figure out what it looks like. I want to find the xy form. So I've got x equals e to the t plus 1 and y equals e to the 3t. I can't easily eliminate a term, so I'm going to try a substitution method. I'm going to take this x and I'm going to solve for t. X minus 1 would be e to the t. And so if I take the natural log of both sides, t is equal to the natural log of x minus 1. So I'm going to plug that in for the t right there. So y equals e to the 3 times ln x minus 1. All right, a little bit of properties of logs here. That multiplier of 3, property of logs, I can put it back up as an exponent. So I have e to the ln, x minus 1 to the third, and that allows the e and the ln, the inverse functions, to act directly one on one another. And I just get y equals x minus 1 cubed. A nice recognizable function. In fact, that's even one I recognize, right? That's just the x cubed graph shifted over 1 to the right. So I know exactly what that's going to look like. And we go over 1 to the right. And there's that sort of classic x cubed graph shape. All right, once again, let's see if we can figure out where we start and stop on this thing. We're supposed to start at t equals 0, and e to the 0 is 1, so that's 1 plus 1, or 2, and y would just be e to the 0, so y is 1. What about when t is ln 2? Let's see, I need to do a little scrap work off to the side here. X would be e to the ln 2 plus 1, which is 2 plus 1, or 3. And y is e to the 3 ln 2. I'm going to use that same log rule. So e to the ln 2 cubed, giving me 2 cubed, or 8. So let's see, I start at time 0 at the point 2, 1. And I end at time ln 2 at the point 3, 8. So I'm only looking at this portion of the curve right in here. And again, this is where we start at t equals 0. This is where we end at t equal ln 2. So we're moving in that direction the entire time. So with these, don't be afraid to play with the algebra. You often have to in order to kind of figure out how to eliminate the parameter and get your xy form. All right, to wrap up this section, example 11 is called Fun with Fancy Curves. Use your calculator or Desmos to graph each of the following curves. Just because it's easier for me instead of flipping back and forth between screens, I went ahead and did these on the calculator, but you absolutely could do them on Desmos as well. Remember, on the calculator, you have to use parametric mode. On Desmos, you just type them in as the x expression, comma, the y expression to get them to graph. So, these are the ones where I kind of already had them in here for us. I'm going to go down here and get rid of the one we were doing a few minutes ago. That was our example. All right. Just to save us a little time, I've typed these in for us already. And I kind of played around a little bit to figure out what the most expedient ranges or intervals would be. On this first one, and again, these are just kind of for fun to let you see how interesting and intricate parametric curves really can get. I've asked us here to graph the function t cosine t, t sine t for x and y. Notice I've got that typed in already. And I want to let my t values go from 0 to 10. Again, I played with this before, so I'm just going to tell you that I kind of figured out that negative 15 to 15 was a pretty good window for x and y. So for my window, 0 to 10 on the t's, leaving the step at whatever they have it on there is fine. I usually like the step around 0.1, and it is. And then I'm going to go ahead and put in the negative 15 to 15 for the x and y. And you'll see we get kind of a spiral here. It only stopped because I stopped it at t equal 10. If I went back and said, let's go bigger, let's go to t equal 20, you'll notice that the spiral is just going to keep on going. In fact, it kind of goes outside the window just a little bit. So A is this kind of cool spiral. B, 2 cotangent t for x and 1 minus cos 2t for y. Our window on the t's is 0 to 2 pi. So again, just to save time, I've already typed those in. Here they are. You'll notice that for x, I had to go with 2 cosine t minus sine t. We don't have a cotangent function on the TI-84. And then here's my y, 1 minus 2, or cosine 2t. So let me fix my window here. We wanted the window to be 0 to 2 pi for the t's. And again, my step is fine. And having played with this before, the x's and y's this time, I'm just going to let them go from -5 to 5. That worked pretty well. And we just sort of get a little hill. Like so. All right, what about C? On this one, they told us to let the t's go from 0 to 6 pi. On this one, I let my x's go from -10 to 60. And I let my y's go from -6 to 6, and it worked out pretty well. So when I go to graph this one, I have it down here as x3 and y3. There's my 3 times t minus sine t, and my 3 times 1 minus cosine t. I'm going to go from 0 to 6 pi as my t window, and -10 to 60 for the x's, -6 to 6 for the y's. You get sort of a bouncing ball phenomenon here, right? Like so. And again, that bouncing ball would keep on bouncing forever if I let my t values keep on going. So, just to show you some kind of fun and interesting functions that we can graph. Some of them are functions, some of them aren't, right? This was actually not a function. As it turned out, it doesn't pass the vertical line test, but these two were. We can actually get some pretty interesting graphs with parametric equations. All right, we will come back next time and we'll talk about doing calculus on parametric functions.